So with this video, I want to talk about salts in the soil. And when I think salts in the soil, what comes to mind immediately is a picture of deserts, irrigation, stunted plant growth because of salinity effects. Also comes to mind what we've talked about, the decline of civilization because of salts and silts. But it turns out there's way more to salts than just this picture. And also, pH plays a very large role in salt-affected soils. So this may be surprising to some of you. So let's first start out with defining what exactly is a salt. Well, a salt is any water-soluble compound that is neutral and that is formed when a hydrogen ion of an acid is replaced by an ion from a base. So, for example, sodium chloride, the salt that we're all familiar with, is formed by the reaction of a base and an acid. But sodium chloride, of course, is not the only salt out there. Any other ion or metallic ion can form. So, for example, ammonia and sulfuric acid will react to a common fertilizer, which is ammonium sulfate, which is a salt. So where all these salts come from is, of course, mostly from the weathering of rock or fertilizer, like here in the last example, or through deposits. So if you're close to the ocean, you get wind and water deposits that might contribute some of these salts to your system. But we don't find them everywhere. We find them, when we do observe them, mostly in landscape depressions. So in valleys where salts that have been freed by weathering up in the highlands accumulate and are showing up in higher concentration in these landscape depressions. And we find them even more prevalent in arid landscapes where precipitation is way less than the potential evapotranspiration, in which we may also have a relatively shallow water table where the salts in that water will be moved upward into the soil system through capillary rise. The salts get rejected by an osmotic barrier in root uptake, so the plant transpires water but leaves the salts preferentially behind. And of course, we also have evaporation from the soil surface, which also leaves behind all these salts, so that over time we accumulate salts in the root zone. So the effects of salts on particular plant growth and thereby also on ecosystems in soils manifests itself in two different ways, and we distinguish them by classifying some soils as saline and some as sodic. Now let's first talk about saline soils. So saline soils are the ones where we have excessive salts of carbonates, chlorides, or sulfates, and the effect on plants and ecosystem is mostly because there's an effect on plant-water relations. So for that, let's review what we know about plant-water relations. We know that in the soil-plant atmosphere continuum, water moves through this plant system in response to gradients in water potential. We have really negative potentials in the atmosphere and then less negative potentials in the plant and eventually in the soil system. So for water to move through the system, of course, water has to move from the soil to the root. And if we recall that this water potential really is a sum of components, where the gravitational, the matrix, the pressure, and the osmotic potential, or the solute potential as we've also called it. Well, as we add salts to the soil solution, we increase this osmotic potential, which makes it so much more difficult for the plant to extract water from the soil, because now this soil potential would be going more negative towards that of the root potential. The gradient would diminish, with that water uptake would diminish. So the osmotic stress that a plant may experience because of the presence of salts in the soil looks very much like a drought stress. So then the salinity reduces the ability of plants to take up water And then this quickly causes a reduction in growth rate, a whole bunch of metabolic changes, and it very much is identical to those caused by water stress. In addition to that, there's also some ionic stress factors where under highly saline conditions, potassium becomes deficient, and that has some implications on plant functioning and toxicity issues. But for the most part, and for purposes of this class, we talk about saline soils, excessive salts of carbonates, chlorides, or sulfates. It is the effect on plant-water relations. A plant will appear to be water stressed when in fact it is a salt stress. Sodic soils, in contrast to saline soils, are not caused by an overabundance of total salts, but rather by a salt imbalance in which sodium is the dominant cation rather than calcium, which tends to dominate most soils. So then in these sodic soils, we have either sodium bicarbonate or sodium carbonate present, which will form sodium hydroxide and gaseous CO2, which will escape into the atmosphere. Either way, the sodium hydroxide is then able to be split, and the hydroxide may react with a proton in solution to form water, or encourage the proton to absorb itself to cation exchange sites. The result of that being that the pH of the soil solution and eventually the soil itself increases, and these sodic soils tend to be dominated by pHs that are upwards of 8, and 8.5 being a pretty typical value for pH of these soils. So the sodium, on the other hand, may attach itself to cation exchange sites, and then eventually the sodium will tend to dominate these cation exchange sites. And we can use a metric called exchangeable sodium percentage to characterize that, and the exchangeable sodium percentage is the percent of sodium occupying the cation exchange site. So quite similar in a sense to the base saturation, except here we're interested in the sodium making up the cation exchange sites. So this exchangeable sodium percentage tends to increase, and we use that as one of the metrics to determine whether a soil is saline or sodic. So having all the sodium on these exchange sites has a physical consequence, and that is that if rather than calcium, magnesium, potassium dominating these exchange sites, sodium dominates these exchange sites, we tend to disperse the colloidal fraction in soils. So we've looked at this previously. For example, when we looked at particle size distribution measurements, we purposefully added sodium to dispersed clay particles so we can measure them individually. The same effect here, the sodium disperses clay particles, they don't stick together anymore. And the consequence for that is that we have a breakdown in the physical structure of soils. So now we have weak structural stability, with everything being dispersed. It tends to clog pores, which causes low hydraulic conductivity and infiltration rates. And then these poor physical properties result in decreased crop productivity caused by, well, we've got poor aeration and reduced water supply. And the low infiltration rates can also cause really severe soil erosion, because now we would generate more runoff in these kind of soils. So the other thing that we might have in the soil is calcium. We might have chloride in there, and if we do, then we are forming the following reaction, in which we form calcium bicarbonate or magnesium carbonate, if that was the cation, and these are solids, so they would precipitate out, and we would have sodium chloride, which would of course add to the osmotic stress and increase what we call the electric conductivity of the soil solution. But it will be a relatively moderate or minor increase in electric conductivity of the solution compared to saline soils, which really tend to have high EC values or electric conductivity values. So forming the solid has the consequence that now in the soil solution, calcium and magnesium as cations are relatively lacking, so they've been precipitated out, they're no longer found in solution. And we can quantify that as what's called the sodium adsorption ratio, which describes the ratio of sodium to calcium and magnesium. And sodium here is the dispersing agent. So it's, if we have more sodium, the soil tends to be dispersant. If we have more calcium, magnesium, it tends to be more flocculating. So this is a metric that helps us determine whether a soil is saline or sodic, and it also says something about how the physical structure of the soil will be affected. Classifying then whether a soil is saline, sodic, or somewhere in between as a saline sodic soil uses the metrics that we've just introduced. So we have the sodium adsorption ratio, the ratio of dispersing to flocculant cations on exchange sites, the electroconductivity, and the exchangeable sodium percentage. So the electroconductivity warrants a little bit more conversation. It's simply a measure of how easily a material conducts an electric current. You probably might remember Ohm's law that says that the flow of electrons is related to a driving gradient, here a voltage drop over some distance, and the factor of proportionality is the electroconductivity, or short EC, that is measured in units of Siemens per meter, or commonly also decisiemens per meter. And this electroconductivity is closely related to the number of electrolytes in solution, and most of these electrolytes tend to be salts in solution. So we can often say that 1 milligram of salts in solution per liter is approximately equivalent to 1/650th decisiemens per meter. And to put this in perspective between rainwater and ocean water, I've put some values down here. Good irrigation water will normally have 0 to 3 decisiemens per meter. If it gets above that, it's normally not very good irrigation water. So speaking of which, if we look on the electroconductivity scale for a moment, you see that there is a horizontal line drawn there at 2 decisiemens per meter. Reason for that is that's normally the cutoff where we say we have some salinity issues and some really salt intolerant plants are going to be affected. But of course there's wide variability in how salinity affects plants. And if we draw a line of an approximate limit for the survival of plants, you'll see that it goes all the way up to an electroconductivity of 7. So for most plants, there's going to be a yield penalty way before you get to 7 decisiemens per meter. A tomato crop, for example, which is going to be quite salt intolerant, will probably already have some yield reductions past 2 to 3 decisiemens per meter, versus a barley, which is relatively salt tolerant, will have probably a 50% yield reduction at a electroconductivity of maybe 5, 6, or 7 decisiemens per meter, but it's still going to be able to function to some extent. Okay. So on this salinity axis, then what we've learned and what we know is that what is causing the yield reduction there is a solute stress. So we increase the osmotic potential, makes it so much harder for the plant to uptake water, and it will look very much like a drought or water stress for the plant. And if we go to the other extreme, so now we are adding more sodium to the soil, we have an imbalance in the salts towards more sodium, and now we've learned that what happens there is that the sodium on the exchange sites will lead to the dispersion of the colloidal fraction, which clogs pores and destroys the soil structure. So some of the aggregation that we've talked about earlier in the semester, these aggregates break apart again and we're losing the beneficial soil structure. If we take this to extremes and we really have a whole lot of sodium with respect to other salts, then there's also some sodium toxicity issues. But normally, before we even get to the sodium toxicity issues, the breakdown in physical conditions of the soil is the major limitation for plants. And then in this somewhere in between range, we also have some nutrient imbalances. We learned about that calcium and magnesium precipitates out and is no longer in solution, and that will of course affect plant growth. So if we are back on the sodium axis, so if we have the detrimental physical conditions leading to the dispersion, then we oftentimes see that on the soil surface as what is called black alkali soils. And what is causing the black surface coating there is the organic matter that was dispersed and is now sort of as a black coating on the soil surface. And in this picture you also see some of the other effects of the structural breakdown on the soil surface. Versus if we have a combination of saline and sodic soils, we often refer to this as white alkali, and here it's really the other salts that are left behind after evaporation from the soil surface and leave this white salt crusting on top of the soil. So then the reclamation of saline and sodic soils really has to follow which one of the two is the dominant limiter for plant growth, and also what kind of soil type you have and what resources are available for the mitigation. So to start out with the saline soil reclamation, the effort here really has to be to bring the osmotic potential down, and you achieve that by leaching out salts from the root zone. So apply irrigation water with the low concentration of salts, for example. You push the salts past the root zone, you've mitigated the salinity issue. Now, of course, some limitations to this, and that is because most often irrigated agriculture with salinity issues tends to be in low-lying areas, so you have a relatively shallow water table, and as you apply more irrigation water in effort to leach salts out, you raise that water table where it comes closer to the surface, and once you've brought it close to the surface, you can no longer use this type of mitigation unless you spend a lot of effort trying to lower the water table again. And this is also one of the reasons for why many irrigated societies, especially ones in Mesopotamia, have failed over time, because you build up salts in your root zone, you try to mitigate for it, and you get to the situation where you have water tables close to the surface and there's no way of leaching the salts out anymore, and your society is going to collapse. So if you have a sodic soil, then the reclamation or improvement of these requires the removal of part, or at least most of the exchangeable sodium, and its replacement by the more favorable calcium ions in the root zone. And there's a whole bunch of different ways of how that can be achieved, and it's going to be dictated sort of by local conditions, what's available, what kind of crops are meant to be grown on this kind of soil. And the way you do this is by amending the soil and by leaching the soil at the same time. So you can use soil amendments such as gypsum or calcium chloride that of course have soluble calcium and making that available to replace the sodium on the cation exchange sites. Or you could use something like sulfuric acid or sulfur, which work somewhat indirectly because they make the insoluble calcium in the soil available again for replacement of sodium. It would also tend to lower the pH. Or you can add organic matter and then have in the decomposition of the organic matter have calcium being freed again that then can replace the sodium on the exchange sites. So the later one, the organic matter, is going to be probably the slowest way to reclaim it, probably the most sustainable one at the same time. So let's take a quick example and look at, well, what if we added calcium carbonate and to a series of reactions would form hydrated lime, and then that hydrated lime would provide a source of calcium that can replace sodium on these exchange sites, and then the sodium would form sodium sulfate, and that sodium sulfate is an aqueous compound, which means that if you now apply irrigation water, you can leach that sodium sulfate out of the root zone, and you've added more calcium to the exchange sites. So this is one way of reclaiming it, but it's a way that doesn't change the pH of the soil. If you add something like sulfuric acid, that will change the pH. The other way you can go about it is to amend this application of hydrated lime with applications of organic matter, which would help not just in the long run, but would also lower the pH at the same time. So most soils though are neither totally saline or totally sodic, so they're somewhere in between, and if they are, then you kind of got to pay attention to the interplay between the dispersing properties of sodium and the aggregating properties of calcium, magnesium, and how that plays together with the electric conductivity of the soil as a whole. So I might be tempted to say I'm going to raise the electric conductivity of the soil, and I'm going to do this by adding more calcium to the soil. That of course would result in better aggregation, so you're mitigating for the detrimental physical conditions. But by raising the electric conductivity, now you've raised the osmotic stress for the plants. So it's an interplay between these two. If you do go the other extreme and you say, well, I'm going to mitigate primarily for the electric conductivity, I'm going to make sure that I have low electric conductivity in my soil by having high amounts of good irrigation water leached to the system, then you tend to disperse the soil. Now you're increasing the relative proportion of sodium because you've leached out the calcium and magnesium, and you have now good osmotic potentials that are not limiting plant growth, but now you've introduced adverse physical conditions by dispersing aggregates in the soil.